In the last video, we came up with the mathematical way to distinguish between the product state versus entangled state. And the distinction came through the properties of the so-called singular values. If the singular values were 1 for one particular uh, case and then 0 for everything else, then we say that the state is a product state. But otherwise, we say that the state is entangled. Okay, so formally speaking, this distinction is, of course, perfectly okay. But in practice, what does it really mean? That some state is entangled and some states are not entangled, but rather is a product state. Okay, so in practice, what is the meaning of a product state? What is the meaning of entanglement? So let me try to build up a case in the context of some thought experiment where this distinction can come to life, product state versus the entangled state. Okay, so let's say we have a n different n different qubits. N qubits. Qubit is just another word for a two-level system. And for each qubit, you can have either a one state or a zero state or a one state, a zero state or a one state, etc. So the wave function for the total n qubit system can be put into this product form. Right, where every SI can be either 0 or 1. And altogether, there are 2 to the n different possibilities of writing down such a product state. Okay, so now suppose such a product state had been prepared by some experiment. And then suppose we did measurement. We measured the state of the first qubit. And then we found that the first qubit was in, let's say, 0 state. Okay. You may have heard that every measurement that we do on a quantum state result in the collapse of the state. Okay, but what exactly does that collapse mean? So I'm gonna first give you a quick explanation of what that collapse means. And actually, it's not that hard to make sense out of that fancy word. So for the first qubit, of course, we have this completeness relation. Sum of the 0 bra and cat plus and the 1 bra and cat is equal to an identity. So anytime we have this state, we can equivalently write this in this form. Okay, so this 0 means the 0 eigenstate for the first qubit, and this is the uh, well, this is the basis one state for the first qubit. Okay, and then you say we measured. We measure that the S1 equals 0, for example. Then what happens is that this, out of these two sort of states which form a superposition, now since we have made this measurement of the first qubit and found it to be 0, it is as if this state is no longer existing in the universe. So we can simply take it out and pretend that this thing never even existed. So then this n qubit state undergoes what's called the collapse to an n minus 1 qubit state, where this n minus qubit state is now given by this. Okay, but notice that this is only the overlap of the first qubit with the 0, so all the other states are still remain intact, S2, S3, etc. So as you can see from the form of these remaining states, you can see that the measurement that we just did on the first qubit did not affect states in the rest of the qubit. Okay, so let me repeat that statement. Suppose initially we had prepared the system in this product of qubit states, and let's say we performed the measurement and found that the first qubit was in a state of 0. Then what happens after the wave function collapse is that simply this state is gone, and what's left behind in that quantum state is just the product of the rest of the qubits. But quite obviously, the state of the qubits before the measurement and after the measurement, well, they're the same. Well, at first you might say, okay, that's kind of obvious. I mean, the only thing that you ever touched was the first qubit, and you never touched the rest of the qubit. So why should you expect the rest of the qubits to be affected by what you did on the first qubit? Well, actually, that things are not that simple for the quantum world. Okay, things are a bit more complicated. That's what people would normally say for an everyday life situation. But in the quantum world, it's more appropriate to say that things are a bit more entangled than you might have imagined from experiences in everyday life. Okay, so let me show you what happens if the states that you had prepared was in an entangled state. And I'll give you the simplest possible example of an entanglement. 0, 1, minus 1, 0. Okay, so that's the spin singlet state that I talked about in the previous video. If you like the spin language more, then this is up, down, minus, down, up. state of the spin known as the spin singlet. Spin singlet. Okay, so this represents the state of the first qubit. This is the state of the second qubit. First qubit, second qubit. Okay, so now suppose you did a measurement and found that the first qubit was in a state of 0. Well, then the wave function would collapse to this, but overlap of the 0 with 1 is 0, so this thing no longer shows up. So after the collapse, you have a 1 for the second qubit. Okay. However, if you measure the first qubit to be in a state of 1, then what that implies is the wave function collapses into this guy, but this overlap will give you minus 0 on the second qubit. Okay, this overall minus sign is irrelevant. So basically means that the second qubit is collapsed into a 0 state. Now that's really very funny, because you can think of these two physical systems 1 and 2 as sort of connected by some sort of invisible bridge, and then you only play with this box and never touch the other box. But nevertheless, depending on what you measure through your microscope on this box, the state of the spin in the second box, for which you have never done any sort of measurement, is changed. The state in the second box is either 1 or 0, depending on what you do or what you measure in the first box. And Einstein, Podolsky, Rosen wrote a paper in 1930 pointing out such consequences for a generic quantum state, and thought that this was really weird, as such things cannot possibly happen in the real world, and therefore the foundation of quantum mechanics has to be questioned. And in their paper, they never claimed that this is a paradox, but everybody since their paper came up decided that this was really strange, and gave it a name, EPR paradox. Well, like all paradoxes, for example, the twin paradox in special relativity, it's not a paradox, but it's just a reality that we find uncomfortable with. But being uncomfortable does not mean that this is wrong. This is actually right. And we just have to find our ways to come to grips with it. Okay, so here, through this simple illustration, you can come up with kind of a practical definition of entanglement, which is the following. If measurement on one subsystem affects states in the other subsystem, then the two subsystems are entangled. Okay. Well, how does this relate to the observation we had made earlier? Well, we showed through a mathematical process that any state can be decomposed in this fashion. Okay, so if more than one state, if more than one of these states has a non-zero singular value, for example, let's say two of these singular values are non-zero, then you can expand the resulting many-body states like this. So again, depending on whether when you do a measurement on the left side of the system, whether the measurement outcome is L1 or L2, the state on the right-hand side of the system becomes either R1 or R2. Okay, so again, what you measure for the left system has a direct consequence on what the state is on the right system. And that's all because we have more than one of these singular values equal to a non-zero number. Okay, so this verbal statement is in complete agreement with the mathematical statement we talked about in the previous video, that having more than one of the singular values being non-zero is the definition of an entangled state. Okay, so now you can make this argument slightly more formal. Because in general, you can write the wave function for the n-qubit system in the following fashion. For the first qubit, the state is either 0 or 1. Okay, so if the state in the first qubit is 0, then the remaining n minus 1 qubit state will be in this sort of wave function. And let me call it psi 0. But if the first qubit was in a state of 1, then the rest of the system would be in the psi 1 wave function, or psi 1 state. So again, depending on whether you measure 0 or 1 for the first qubit, the wave function collapse is either from psi n to psi 0 n minus 1, or from psi n to psi 1 n minus 1. So which of these collapses will occur depends completely on what you measure for the state of the first qubit. Okay, so this seems puzzling because we have tried to understand this phenomenon in terms of the sort of everyday language. And then when you put it like that, in terms of the everyday language, it seems really strange. However, none of us has really lived down deep down in the quantum world, so we don't really know from experience how the quantum world operates. So if this is what the system of quantum mechanics tells us, then presumably this is a sort of understanding that we have to take for granted. Okay, but okay, so the entanglement is puzzling, or at least at first sight. But what people came to realize over the years is that entanglement is also very useful. Why? Because you can control the states of the remaining n minus 1 qubits without actually controlling them, without actually touching them. Instead, all you have to touch is the state on the first qubit. So let me put it bluntly. If the n particle n qubit state is given in this fashion, so good is the good state for the n minus 1 qubits, and bad is the bad state for the n minus 1 qubits. And you want to be certain that the n minus 1 qubits are thrown into the good states and stay away from the bad state. Well, there's a way to ensure good. Because to ensure that the good state is always realized for the n minus 1 qubits, all you have to do is make measurements on the first qubit in such a way that the result will always be 1. Okay, so if you can set up your device in such a way that you have the guarantee of finding always the 0 state for the first qubit, then automatically this part of the wave function will never be the wave function that the state collapses into. The wave function will only collapse into this because you have measured this. Okay, that sounds pretty good. Okay, so let me make this a statement slightly more concrete with some mathematical example. Okay, so let me try to push through this idea. Okay, so for the two-level system, I have talked a lot about this completeness relation. Okay, and since this is an identity, multiplying u dagger on the left of the identity and u on the right side of the identity, or maybe the other way, is not going to change the fact that this is an identity. And on the right hand side over here, that's like saying this. Okay. So the state 0 acted on by some unitary matrix is going to be called u0. And this is nothing but the conjugate of that, so I'm going to put bra instead of a cat around it. And this thing will be called u1, and this will be the u1 with the arrow going the other way, like this. Okay, so this is still an identity. So let's say we apply this identity to some state. Okay, and let me choose this state to be the good old singlet state. Okay. Now, this is the same as u0. Oops. This is the same as u0, u0 psi plus u1, u1 psi. Okay, just writing down the identity. This plus that is an identity. And then suppose that you have made some measurement. You measure the state of the first qubit in a way which intentionally finds the first qubit to be always in the state of u0. Okay, so u0 is u acting on the 0, and then 0 is spin up. So applying this unitary matrix to the spin up is like making some sort of rotation of the spin orientation from the up direction to some arbitrary direction on the Bloch sphere. Okay, so let's say you do that. Then, as a consequence, the wave function will collapse into u0 overlap with the original state. But remember that my original state was this singlet state. So now it's a u0 overlap with the 0, 1. That's the state of the second qubit, minus u0 overlap with 1 times 0. This is also the state of the second qubit. Okay, so now after the measurements on the state of the first qubit, the second qubit is collapsed into this kind of state with the mixing coefficients given by this number and this number. Okay, actually these overlaps are easily calculable because this is 0, u dagger 0, and you know what u dagger looks like, and then the 0 is just a column vector with elements 1 and 0. So after some exercise, you find that this is cosine half theta, and then this overlap will give you sine of half theta with this phase factor. Okay, so now that means that this collapse wave function is cosine of half theta 1 minus e of minus I phi sine of half theta 0. Okay, but after some more calculation, you can also find that this is the same as the u acting on the one state, which is the spin down state. Okay, so this going from here to here is just some mathematical check. Okay, so one is the same as the spin down state. So this also represents some sort of rotation of the spin initially pointing down along the minus z direction into some other direction as dictated by the elements of this unitary matrix. Okay, so that means by controlling the nature of this u, we can force the second qubit or the second spin to be in whatever state we want, because this state can be anywhere on my block sphere. So initially this was the state of the second qubit, but because of the action of the unitary matrix, now this spin can point anywhere on the block sphere, which means if we have can exercise a careful control on the unitary matrix, then we can place the second qubit to be in whichever direction we want it to be without actually having to exercise any sort of direct control over the second qubit. All you have to do is to exercise a careful control on the measurement of the first qubit, so that the outcome of the measurement of the first qubit will always be the u0. Okay, so I hope you can get a flavor of what this entanglement feature can bring to us in terms of having a delicate control over the quantum system by simply touching the part which does not belong to the system. Okay, let me just repeat it one more time. If you want to have a careful control over the state of the second spin, then all you have to do is to exercise a careful control over the measurement of the first spin. However, there's one important caveat here, namely, such sort of control will not be happening unless the state itself was entangled. If the states are not entangled, but a simple product state, then no matter what you end up measuring for the first qubit will have no consequence whatsoever for the state of the rest of the qubits. In other words, entanglement is a gift that we can use wisely to have a control on the quantum system in a way that no delicate piece of machinery can allow us to have. That's why the quantum information science is so puzzling, but also so exciting at the same time.